In this video, I am going to teach you the dispersion measurement in optical fiber. In the previous video, I have taught you what is dispersion and what are the types of the dispersion. As we all know that there are the two types of the dispersion, intermodal dispersion and chromatic dispersion. Chromatic dispersion is also known as a intramodal dispersion, and here we have time domain intermodal dispersion measurement, frequency domain intermodal dispersion measurement, and for the intramodal we have the chromatic dispersion measurement. Now let's get started with the time domain intermodal dispersion measurement. So in time domain intermodal dispersion measurement, we have the electrical pulse block, laser diode block, mode scrambler, variable delay, fiber under test, and optical sampling oscilloscope. So this block is used to generate the electrical pulses, and there are the two links, optical link and electrical link. This link is used to carry the electrical pulses. So optical link will carry the electrical pulse from electrical pulse block to the laser diode. Now the function of the laser diode is to convert the electrical pulses into the light signal, and the output of the laser diode, that is the light signal, is given to the mode scrambler. Mode scrambler is used to scramble the modes. As we all know that we are dealing with the intermodal dispersion, and it happens in the multimode fibers. In multimode fiber we have the different modes. So for that we have the mode scrambler. Mode scrambler is used to select the number of the modes for the optical fiber cable, and we have the optical fiber cable, and in this we are going to test the dispersion. Now the output of the mode scrambler is given to the optical fiber, and the output of the optical fiber is given to the optical input of the oscilloscope. Now here we can see that electrical pulse block generate the electrical pulses, and with the help of the electrical link, electrical pulses will go from the electrical pulse block to the variable delay, and the output of the variable delay is given to the electrical input of the oscilloscope. Now here the difference between the optical input and the electrical input gets calculated, and here we can see that this is the electric pulse, original electric pulse, which was given here and here, and this is the dispersed signal which we got from this fiber optic cable. So with this we can measure the dispersion with respect to the time domain. So if we draw the uh, graph of the time domain intermodal dispersion, so it will look like this. Like this is the y-axis and this is the x-axis. On y-axis we will have the amplitude, and on x-axis we have the time domain. So this is the electrical pulse and this is the dispersed pulse. So the graph of the time domain intermodal dispersion will look like this. And this was a simple explanation of this block diagram. Now let's get started with the frequency domain intermodal dispersion. So in frequency domain intermodal dispersion, as you can see here, all the block diagrams are same till here. All the block diagrams are same in this, except spectrum analyzer here is present. And in the time domain we have the oscilloscope, and here we have the spectrum analyzer. So now the question arises that why we are using this spectrum analyzer, not the oscilloscope, to measure the frequency. So those who don't know, I will tell you that oscilloscope only supports the measurement in the time domain. It does not support the measurement in the frequency domain. So that's why we are using the spectrum analyzer. So here what will happen is that uh, in here we will get the optical input, and here we will get the electrical input, and these two inputs will get compared, and here we can see the dispersed signal, and here is the electrical signal, original electrical signal. And this was the simple explanation of the frequency domain. And the graph of the frequency domain intermodal dispersion will look like this. Suppose this is the y-axis and this is the x-axis. Here we will have the amplitude and here we will have frequency. Now the signal will look like this input signal. This is the input signal and this is the output signal, dispersed signal. This is the input and this is the output. And this was a simple explanation of the frequency domain intermodal dispersion measurement. Now for the intramodal dispersion measurement, that is the chromatic dispersion measurement. That is the chromatic dispersion measurement. So chromatic dispersion measurement happens in single mode optical fiber. So for that we have the tunable narrowband optical source. It is used to generate the single mode uh, laser signal, and this signal is given to the optical coupler. An optical coupler will have the wavelength meter, which is used to uh, show the wavelength of the signal, light signal, and the output of this is given to the intensity modulator. An intensity modulator will modulate the intensity of the light signal with the help with respect to the electrical source. With respect to the electrical source, here you can see that electrical source is given here, arrow is pointing here. So intensity of the light signal will get modulated with respect to the electrical source, and here uh, the fiber through the fiber which we want to test the, or we can say that we want to measure the dispersion, we will have this fiber here, and the output of the fiber will go to the photoreceiver. Now the function of the photoreceiver is to convert the light signal into the electrical signal, and here the output of the photoreceiver will be the electrical signal, and here the electrical source will give the electrical signal to the phase comparator. Or you can say that it will give the electrical pulse to the phase comparator, and the phase comparator will compare the electrical signal which is coming from the electrical source and the electrical signal which is coming from the photoreceiver block, and it will give the uh, it, it will give the measurement of the dispersion. The output of the phase comparator will give the measurement of the dispersion. Here in this diagram we can see that this is the group delay, this is the group delay, and this is the dispersion. And this is the simple explanation of the chromatic dispersion measurement.